In this video we're going to look at how Newton's third law can be combined with Newton's second law to enable us to answer a wider range of problems. So Newton's third law states that if a body A exerts a force on a body B, then body B is going to exert an equal and opposite force on body A. Now often this is going to be when the two bodies are actually in contact with each other. But Newton's third law is also true for any two objects regardless of whether they are touching or not. As one example of this, just consider two magnets which are arranged with opposite poles facing each other. Then the two magnets are going to attract each other. Newton's third law implies that the force of attraction that magnet A experiences due to the presence of magnet B will be equal but opposite to the direction of the force of attraction that magnet B experiences due to the presence of magnet A. So, we're now going to have a look at a couple of examples in which our knowledge of Newton's third law is going to be crucial. We've got a parcel of mass 2 kilograms rests on the floor of a lift of mass 100 kilograms which is accelerating upwards at 3 meters per second squared. The first thing we're being asked to do is draw a force diagram to show the forces acting on the parcel and determine the contact force between the lift floor and the parcel. So, there's my simple diagram of the lift together with the parcel inside the lift, and in this diagram we are only going to show the forces acting on the parcel. So the forces acting on the parcel are its weight, which is 2 times 9.8 or 19.6 newtons, and then the contact force, which we'd normally call the reaction force, from the lift floor onto the parcel. So there's our reaction force. We know that the parcel is inside the lift and that the lift is accelerating upwards at 3 meters per second squared, which means that the parcel is accelerating upwards at 3 meters per second squared. So applying Newton's second law upwards, we have R minus 19.6 must equal the mass of the parcel, which is 2 times by 3. In other words, the reaction force must be 25.6 newtons. For part B, we've got to draw a force diagram to show the forces acting on the lift alone, and hence find the tension in the lift cable. So again, we'll start with a diagram. And in this case we are concentrating on the forces acting on the lift only. Forces acting on the lift only, well, we've got the weight of the lift, and the lift has a mass of 100 kilograms, so its weight is 100 times 9.8 or 980 newtons. There'll be the tension in the lift cable, but there will also be, since we are considering the lift only and not the lift and parcel together, there'll also be the force of the parcel acting down on the lift, which will be equal and opposite, by Newton's third law, to the contact force of the lift on the parcel. So we've got this force R acting down on the lift floor from the parcel. We know the lift is accelerating upwards at 3 meters per second squared. So we can now apply Newton's second law vertically and obtain T minus R minus the weight of the lift must equal 100 times 3. So that gives me T minus 25.6 minus 980 equals 300. In other words, the tension in the lift cable must be 1305.6 newtons. For part C now, we've got to draw a force diagram showing the external forces acting on the combined system consisting of the lift and the parcel together, and use this diagram to check your previous answer for the tension. So, for the combined system, we have got the forces are the weight of the parcel, the weight of the lift, and the tension in the cable. We don't show the reaction or the contact force of the lift on the parcel, or the effect of the parcel forcing down on the lift, because they are equal and opposite forces. They are internal forces for the whole system, so we can ignore those because Newton's third law tells us that they are equal and opposite. For the whole system, we know it's accelerating upwards at 3 meters per second squared. So applying Newton's second law to the whole system, we've got T minus the weight of the lift minus the weight of the parcel must equal 102, that's the mass of the whole system, times by 3. So that gives me T minus 980 minus 19.6 equals 306. In other words, T is 1305.6 newtons, exactly as we had when we considered the lift only. For our second example, we've got a car of mass 800 kilograms moves along a horizontal road, pulling a trailer of mass 200 kilograms. If the car and the trailer are accelerating at 0.6 meters per second squared, when the resistance to the car's motion is 750 newtons, and the resistance to the trailer's motion is 250 newtons, we've got to find the driving force produced by the car's engine and the force in the tow bar linking the car to the trailer. Now, on questions like this, where there's been no guidance given in terms of which order to apply Newton's second law, my suggestion to you is to apply Newton's second law first to the whole system. So if we consider the whole system, we know it's accelerating at 0.6 meters per second squared. We know that the car is producing a driving force of D, that there's a resistance to the car's motion of 750 newtons, and that there's a resistance to the trailer's motion of 250 newtons. Now again, just to emphasize, at this stage we are only considering the whole system of the car and the trailer. Because we're considering the whole system of car and trailer, we don't need to worry about the force in the tow bar, because that is an internal force. The car is going to be experiencing an internal force to the left from the tow bar, whilst the trailer is going to be experiencing an internal force to the right along the tow bar. These are equal and opposite by Newton's third law, so we don't show them on the combined system. What's more, in this diagram we have simplified things by ignoring all of the vertical forces acting, because all of the interesting motion is along a horizontal road, so the vertical forces don't come into account. So applying now Newton's second law horizontally, we have D minus 750 minus 250 is the resultant force, must be equal to the mass of the whole system, which is 1000, times by the acceleration, which is 0.6, which gives me D equals 1600 newtons. If I want to find the force in the tow bar linking the car to the trailer, then I need to consider one of the components of the system separately. In this case, it's easiest just to consider the trailer. So if we just consider the trailer, the only forces actually acting on the trailer are the force in the tow bar, which is pulling the trailer along, together with the resistance force of 250 newtons. We know that the trailer is accelerating at 0.6 meters per second squared. So we've got from Newton's second law, T minus 250 newtons must equal 200 times by 0.6. In other words, the tension in the tow bar must be 370 newtons. We could check these answers are correct by drawing the force diagram for the car only and applying Newton's second law to that. I suggest you just pause the video for a moment or two and just check that that also gives you a value of T as being 370 newtons. Moving on from there, to finish the video, there are two questions here. So what I'd like you to do at this stage is just pause the video and work your way through these two questions, and then you'll be able to discuss them in class at your next lesson. And that concludes our look at Newton's third law.